Hi everyone, and welcome back to Lecture 3 in our series on AI in Railways and System Assurance. Now, just to recap where we have been, in Lecture 1 we looked at the real world, the actual examples of AI in maintenance, safety and operations, along with those tricky assurance challenges. Then, in Lecture 2 we went deep, we looked at the Senelec RAMS framework, specifically EN 500, 126, 128 and 129. We showed that even in the age of AI, these standards still work provided we are thoughtful about how we extend them. Today, we are zooming out. We're going to look at the wider AI standards and the regulatory landscape, specifically 4 key areas. First, there is ISO 42001. Think of it as a management system for AI, similar to ISO 9001. Then, we have ISO 23894, which focuses on risk management. We'll also be talking about the EU AI Act. This is a landmark piece of regulation because it officially classifies AI in railways as high risk. And finally, we'll look at the RSSB toolkits, the rail-specific guidance coming out of the UK. Ultimately, we are here to answer one big practical question. How do I combine the traditional Senelec standards with these new AI regulations to build one coherent assurance framework? By the end of this session, you'll see exactly how these pieces fit together and how they impact the way we design, deploy, and operate AI systems in the rail industry at work. Now, at this point, you might be thinking, wait a second, if the Senelec standards are still valid, why do we even need these new AI standards at all? It's a fair question. The short answer is this: Senelec gives us the RAMS skeleton. It's the framework, but AI introduces a whole new set of issues, things like data bias and model drift, that need their own specific language and governance. You see, the traditional Senelec standards were written primarily for deterministic hardware and software. They basically assume that once a system is deployed, its behavior stays static. What they don't explicitly talk about are things like data bias, model drift, explainability, or how much human oversight is actually required for an AI. That's exactly where these new standards and regulations come in to fill the gaps. For example, ISO 42001 gives you a management system. It's about how your entire organization governs AI projects. Then you have ISO 23394, which gives you a risk management vocabulary specifically tailored for AI issues, like adversarial attacks or bias. Then there's the EU AI Act. This brings in the regulatory consequences. If you're using AI in certain roles in the rail industry, you're officially in a high risk category, and that comes with very specific legal obligations. And finally, the RSSB toolkits take all these high-level ideas and translate them back into railway language, giving us practical checklists and templates we can actually use. So the key takeaway here is that we aren't replacing Senelec, we're augmenting it. We're adding these AI-specific management and regulatory layers on top of that solid RAMS foundation at devs. Think of AI assurance as 4 distinct layers that all have to align perfectly. Right at the base, the foundation, you have your operational practices. This is the day-to-day stuff, monitoring how the model is actually performing, logging every prediction and outcome, and having a solid plan for handling any incidents or near misses. It's also about knowing how to retrain and redeploy those models safely when they start to drift. Sitting right on top of that base, you have the Senelec RAMS standards. This is the world of EN 50126, 50128, and 50129. These are what give you that structured engineering and assurance process. It's how we handle the RAMS lifecycle, software development, and the safety cases we are all familiar with. Now, as we move up to the third layer, we bring in ISO 42001 and 23894. These standards define the big picture, how an organization should govern AI across all its projects, not just one at a time. It's about managing AI-specific risks systematically across the whole company. And finally, on the very top, we have regulation. This is the EU AI Act, along with national laws and sector-specific guidance. These set the minimum mandatory requirements, especially for systems that are deemed high risk, like safety functions in rail. The key message I want you to take away is this: no single standard is enough on its own. If you want a robust assurance strategy for real AI, you have to use all four layers together. And nuts. Next, let's talk about ISO 42001. You can think of this as the ISO 9001 for AI. It's an AI management system standard, but it's been specifically tailored to handle the unique challenges that come with artificial intelligence. The first thing to understand is that this isn't just about a single project, it's organization-wide. It defines how you plan, implement, operate, monitor, and improve your AI systems in a truly structured way. Essentially, it's built around the plan, do, check, act cycle, or PDCA. Here's how that looks in practice. First, you plan. You define your policies, your roles, and your risk criteria for AI. Then you do. You actually implement the AI systems following those policies you just set. Next, you check. You monitor the performance, keep an eye on incidents, and ensure you're staying compliant. And finally, you act. You take what you have learned and use it to improve your policies and processes. For those of us in the railway sector, ISO 42001 is really about embedding AI governance right into your existing safety management system. It ensures that every AI project, no matter how big or small, follows the same consistent, well-controlled practices across the board. To make ISO 42001 work for rail, we need to focus on four core themes. First, there is governance and responsibility. This is all about the who. Who is the AI owner? Who is responsible for the risk assessments, the approvals, and the ongoing monitoring? It's about setting up an AI governance board or something similar and ensuring you have top management commitment. Because in a safety critical industry like ours, AI simply cannot be a side project. Second, we have risk management integration. We aren't building a new silo here. We're integrating AI risk into our existing enterprise and safety management systems. That means aligning everything with the frameworks we already use, like EN 50126 HARA and the Common Safety Method or CSM RIA. The third theme is data and model management. This is the nuts and bolts your policies for how data is collected, labeled, and stored. You need standard procedures for the entire life cycle, from training and validation all the way to deployment and retirement. And of course, clear versioning and documentation is a must. Finally, we have human oversight and ethics. We need to build in human-in-the-loop mechanisms wherever they are needed. This also covers policies on fairness, transparency, and non-discrimination, especially when AI decisions affect our staff, our passengers, or the general public. This actually aligns really well with the RSSB's human factors work that we'll look at a bit later. Ultimately, for a railway, adopting ISO 42001 is about a mindset shift. It's about moving away from we built an AI prototype and moving toward we systematically govern AI across our entire organization. Now let's move on to ISO 23894. This standard is all about risk management specifically for AI. Think of it as the bridge between general risk standards like ISO 31000 and the very unique challenges that AI brings to the table. It follows a clear 5-step cycle. First, you have to identify the risks, and this is where things get interesting because we're looking for things like data bias, where certain conditions are underrepresented, and model drift, which is that performance degradation we see over time. We also need to watch for distributional shifts, where the real-world environment starts looking different from our training data, and of course those tricky human-AI interaction problems like automation bias or overtrust. Second, we analyze. We need to get to the bottom of these risks, understanding their causes, their likelihood, and their consequences. We're looking at both the technical side and the socio-technical factors. Third, we evaluate. This is where you decide which risks are acceptable and which ones require treatment. It's very similar to the process in EN 50126, but with a dedicated AI focus. Fourth, we treat the risk. This means mitigating by design using things like data diversification, robustness techniques, and confidence thresholds. But it's also about organizational controls like specialized training and human oversight. And finally, we monitor and review. AI isn't a set it and forget it technology. You have to track this risk over time. New hazards will appear, and old ones might change in importance. You need to take that real-world operational experience and feed it right back into your risk register. The big takeaway here is that ISO 23894 gives you the risk vocabulary you need. You can take these AI-specific terms and plug them directly into your EN 50126 HERA to make your safety case complete nights. Now let's look at how we actually put this into practice. We can map ISO 23894 directly onto the HERA cycle from EN 50126 that we talked about back in lecture 2. The idea here isn't to reinvent the wheel, it's about enhancement. For instance, when EN 50126 tells you to identify hazards, ISO 23894 is there to prompt you to include AI-specific hazards, moving beyond just the traditional ones. When the standard says to assess the risk, ISO 23894 provides the guidance you need to consider things like bias, model drift, adversarial factors, and those complex human-AI interactions. When it's time to define your controls, ISO 23894 suggests specific AI measures, things like data governance, robustness techniques, and monitoring strategies. Then, when you move to verify those controls, the AI standard points you toward model validation, scenario-based testing, and continuous field monitoring. And finally, when EN 50126 says you need to document everything, ISO 23894 expects a dedicated AI risk register with full traceability back to your evidence and mitigations. So, the key takeaway is this: you don't need to run two separate risk processes. Instead, you simply extend your EN 50126 workflow by plugging in the AI risk concepts from ISO 23894. It's about making your existing process smarter, not more complicated than once. Now, we need to talk about the EU AI Act. This is the first comprehensive AI regulation of its kind, and for the railway industry, there is one very important message you need to take away. Many of our rail AI systems are going to fall squarely into the high-risk category. Specifically, the Act treats AI as high-risk in two main scenarios. First, if it's a safety component of a system already regulated under rail safety law, or second, if it's used to manage and operate critical infrastructure safely. To give you some concrete examples, we are talking about AI used for obstacle detection at level crossings, especially if that detection influences braking or signaling. We are talking about AI in traffic management that directly affects train movements, or AI used in safety monitoring where a failure could materially increase the risk of an accident. If your system is flagged as high risk, it's subject to some very strict requirements. You'll need a conformity assessment before it even hits the market. You'll need rigorous technical documentation, traceability, and logging. You will have to implement a quality management system for the entire AI lifecycle, and you'll have ongoing post-market monitoring obligations. Essentially, if you are designing AI for safety-related rail functions, the EU AI Act is no longer optional. It becomes just as important to your project as the Senelec standards themselves. In its simplest form, if you're working with high-risk AI under the EU AI Act, there are 6 core obligations you have to satisfy. First, you need a risk management system. This is a structured process to identify, analyze, and mitigate risks across the entire life cycle. The good news here, this dovetails perfectly with what we have already discussed in EN 50126 and ISO 23894. Second is data governance and quality. Your training, validation, and testing data have to be appropriate for the context. They must be representative and as much as possible free of undue bias. And of course, everything has to be managed securely. Next, we have technical documentation and traceability. This means keeping detailed records of your model design, your training data sources, and your performance metrics. You need enough detail so that regulators and assessors can actually step in, understand what you've built, and audit it effectively. Fourth is logging and monitoring. You need logs that show exactly how the AI is being used and how it's performing in the field. This is vital for post-market surveillance and investigating any incidents that might occur. Then there's human oversight. There must be clear mechanisms in place so that humans can understand the AI's output, override it if necessary, and ultimately prevent or minimize risk before they escalate. And finally, the system must prove its accuracy, robustness, and cybersecurity. The AI has to be resilient, not just against technical failures, but against deliberate attacks or manipulation. Now, if you compare this list to the standards we have already looked at, you will notice a lot of overlap. The real trick to success here is alignment. You want to design your processes so that one single set of evidence can satisfy multiple obligations at once. To see how this all actually works in the real world, let's revisit our level crossing obstacle detection example and apply the EU AI Act framework to it. First, let's look at risk management. In a traditional EN 50126 HERA, you'd identify a primary hazard. The AI fails to detect a vehicle, leading to a collision. But when we bring in ISO 23894, we expand that. We start asking about AI-specific issues like unusual weather conditions, camera occlusions, or even adversarial factors. The AI Act essentially expects you to have a documented system that tracks these risks from start to finish. Next is data governance. This is where we curate our dataset. We don't just need pictures of cars, we need a diverse range of images, different times of day, different weather, and every vehicle type from motorbikes to heavy trailers. We have to document exactly how we label this data and prove that it's truly representative of the real-world conditions that train will face. Then we have the technical documentation. This is your model's biography. You're documenting the architecture, the training process, and crucially, the performance metrics for specific scenarios like heavy rain or fog. You have to be very clear about the limitations. For instance, if the system's accuracy drops during a heavy snowstorm, that needs to be stated upfront. For logging and monitoring, imagine every single detection being logged with a timestamp, a confidence score, and the resulting alert. By logging near misses as well as actual incidents, you create a feedback loop. You can use those logs to fine-tune your thresholds or decide exactly when it's time to trigger a retraining of the model. Finally, we have human oversight. Even with a smart AI, the control room operators are still the ultimate decision makers. The interface needs to show them why the AI is alerting, perhaps using bounding boxes around objects, so they can make an informed choice. You need clear procedures that define exactly when to slow or stop traffic based on those alerts. So as you can see, satisfying the EU AI Act isn't about doing a bunch of extra random tasks. It's really about a disciplined, combined application of Senelec and the ISO AI standards, backed up by some very clear governance and documentation. Now, specifically in the UK, the RSSB, the Rail Safety and Standards Board, has been doing some really valuable rail-focused research. They have developed guidance that is tailored specifically to our industry. There are 3 projects in particular that you should have on your radar. First, there is Project T1362, which focuses on human factors and AI. This is all about the interaction between humans and AI in a rail context, whether that is in control rooms, maintenance, or safety monitoring. It provides a set of principles for designing AI that supports rather than replaces humans, and it gives us strategies to avoid the pitfalls of over-automation. Next, we have Project T1363, the AI Change Toolkit. This is a question-based framework that has been aligned with the Common Safety Method, or CSMREA. It helps rail organizations answer the really practical questions. Things like, is this AI change actually safety relevant? Or what kind of reassessment do we need to do? It basically gives you a roadmap for structuring the whole change process. And finally, there is T1364, which looks at the AI standards landscape. This project does the heavy lifting of mapping those general standards we talked about, like ISO 42001 and the EU AI Act, directly onto Rail use cases and Senelec. Essentially, it tells you if you're building this type of application in Rail, these are the standards you need to follow and how they all fit together. At the end of the day, these toolkits are designed to be the bridge. They help practitioners like us cross over from generic high-level AI standards to successful real-world Rail projects. Now, the T1363 AI Change Toolkit is a particularly useful piece of kit. It's designed to help you align your AI deployment with European railway safety regulations and specifically the CSM REA. As many of you know, the CSM REA requires a very structured process. You have to evaluate every change to the rail system, decide if that change is significant, and then document all the hazards and controls. This is where the AI Change Toolkit comes in. It provides you with a set of structured questions to help you assess whether introducing or modifying an AI system does three things. First, does it alter any safety functions? Second, does it change human tasks or responsibilities? And third, could it introduce any new systematic failure modes? If the toolkit comes back and says, yes, this AI change can affect safety, then your path is clear. You treat it as a significant change under CSM REA. You apply the EN 50126 HERA, but you make sure to extend it with those ISO 23894 AI risk concepts we talked about. And finally, you build or update your EN 50129 safety case to reflect the new AI reality. So, the big takeaway for T1363 is that it doesn't replace Senelec or the CSM. Instead, it's a diagnostic tool. It helps you decide exactly when and how intensively you need to apply those standards to your AI project. Finally, let's look at project T1362, which focuses on the human factors in AI. If there's one thing to remember from this section, it's these three core principles. First, we have human in command. The philosophy here is simple. AI should support, not replace, the critical human roles in our safety and operations. Think back to that intelligent junction optimizer we discussed in lecture 1. The root controller is still the one in charge. They remain responsible, while the AI simply acts as a powerful assistant, proposing the best options for them to consider. Second is transparency. It's vital that our operators understand three things: what the AI is doing, why it's making a specific recommendation, and where its limitations actually lie. A great example of this is a trespass detection system. It shouldn't just pop up a message saying 89% chance of trespass. It should show the operator exactly which region of the video feed triggered that alert so they can verify it instantly. Third, we have the concept of calibrated trust. This is all about finding the Goldilocks zone. We want to avoid overtrust, where operators blindly follow the AI even when it's wrong, but we also want to avoid undertrust, where they ignore the AI even when it's providing valuable insights. We achieve this through better training and UI design, things like showing the AI's confidence level and making it easy for the operator to cross-check the AI's output with the raw data. In practice, T1362 provides the design questions and patterns you need to ensure your AI implementations actually align with human capabilities rather than undermining them. And importantly, this work directly supports the human oversight requirements we see in both the Senelec standards and the EU AI Act. So, let's take everything we have discussed and put the whole governance picture together for a railway deploying AI. Think of it as a three-tier strategy. First, at the project level, for every specific AI system you build, you're still going to apply the Senelec standards. EN 50126 for the lifecycle, 128 for software, and 129 for your safety case. But now, you're going to extend that foundation with ISO 23894 to make sure you have captured every AI-specific risk. Second, we move up to the organizational level. This is where you implement ISO 42001 as your AI management system. This isn't just a separate folder on a server, It's about your overall governance structures, your AI policies, and your data management practices. The goal here is to integrate these AI-specific rules right into your existing safety management system. Third, we look at the regulatory level. You'll need to view every system through the lens of the EU AI Act. You have to identify which systems are high risk and ensure they meet the strict requirements for documentation, monitoring, and conformity. And of course, you'll use the CSM-REA to structure your risk evaluations whenever an AI change impacts the wider system. Finally, don't forget your Rail-specific support. Use those RSSB toolkits we talked about, 13, 62, 63, and 64, along with any national guidance. They are there to help you translate these abstract, high-level standards into concrete Rail practices. If there is one message I want you to take away from this lecture, it's this. You don't need to reinvent the wheel for AI assurance. All the parts you need already exist. Your job and the real challenge is simply to combine them into one coherent, robust framework. To wrap things up, let's bring back our wheel degradation AI system one last time and see exactly how each piece of the puzzle we've discussed today applies to it. First, we have our familiar CENELEC standards. EN 50126 treats the detection of wheel defects as a system with specific hazards and RAMs requirements. 50128 governs how we develop and verify the actual model, and 50129 is what we use to build a safety case proving that the risk of derailment from a wheel defect is being acceptably controlled. But then we add ISO 23894. This is where we look for the AI-specific gotchas. We check for data bias. For instance, are some of our older fleets underrepresented in the training data? We watch for model drift. Maybe a new wheel supplier changes the wear patterns the AI was trained on. And we look at human-AI miscommunication. Are our maintainers actually understanding those risk scores correctly? Next, we look at the organizational level with ISO 42001. This ensures there is a solid policy in place for how these models are updated, who exactly has the authority to approve a model change, and how any incidents are escalated and investigated across the whole company. If this system is judged as high risk under the EU AI Act, we add another layer of accountability. We'll need a documented risk management system, technical documentation that's ready for a regulator to inspect, and ongoing post-market monitoring. Most importantly, it ensures human oversight, making sure the maintainers stay in control while the AI acts as their advisor. And finally, we look to the RSSB toolkits. T1363 helps us decide if this new system is a significant change that triggers a full CSM-REA assessment. Meanwhile, T1362 guides the design of the interface, ensuring our maintainers trust the AI just enough but not blindly. As this case study shows, these emerging AI standards and regulations aren't here to replace our Rail framework. They are here to plug into it, making our system smarter, safer, and more reliable. Before we wrap up, I want to leave you with 3 common pitfalls that I see people fall into when they start working with AI in Rail. The first is treating AI as just another software module. Now, strictly speaking, yes, AI is software, but it's a different beast. It's data dependent, it's probabilistic, and it's constantly evolving. If you apply EN 50128 in a vacuum without ISO 23894 or proper AI governance, you are going to miss those critical risks like data bias and model drift. You can't just treat it like a static piece of code. The second pitfall is tick box compliance. It's very tempting to say, okay, we have got our checklists for CENELEC and the EU AI Act, let's just tick the boxes and call it a day. But that mindset only leads to paper safety, not real safety. You have to keep thinking critically. You have to ask, what are this specific system's true failure modes? And are our controls actually effective in the real world, or do they just look good on a spreadsheet? Finally, there is the danger of ignoring human and organizational factors. AI fundamentally changes how people work, their responsibilities, their workload, and the skills they need. If you ignore human factors and change management, you're asking for trouble. You risk creating automation bias, where people trust the AI too much, or the opposite, where the tools aren't trusted or understood at all. Either way, you end up with organizational friction and workarounds that eventually undermine safety. At the end of the day, real assurance isn't just about following the rules. It comes from combining compliance with thoughtful, risk-driven engineering and human-centered design. If your railway organization is just starting to adopt AI, I want to leave you with a practical roadmap to follow. This isn't about deploying AI overnight, it's about preparing your organization so that when the projects do arrive, you're ready to handle them systematically and safely. Here are the 6 steps you should take. Step 1. Inventory your AI systems and pilots. Start by listing every current and planned use of AI across the board, from maintenance and operations to your back office systems. You need to know exactly what's on your plate. Step 2. Classify the risk. For every system on that list, you need to decide, is it safety related? Does it fall into a high risk category under the EU AI Act? And is it a significant change under CSM REA? I highly recommend using the T1363 toolkit to help structure this process. Step 3. Establish your AI governance. Designate an AI governance lead or a committee. Start drafting high-level policies inspired by ISO 42001, specifically around data management, model updates, and how you expect to monitor these systems once they are live. Step 4. Integrate AI into your HERA. Don't wait for a project to start. Extend your EN 50126 hazard templates now to include AI-specific failure modes like bias, drift, and ODD violations. Use ISO 23894 as your risk management handbook here. Step 5. Update your safety case templates. Make things like data lineage, the model lifecycle, and monitoring plans standard sections in your EN 50129 safety cases. This ensures that every project team knows exactly what evidence they need to provide from day one. And finally, step 6, train your staff. This is crucial. You need to give your engineers, safety assessors, and operators a solid foundation. They need to understand the basics of AI, its limitations, and most importantly, the human factors from T1362 on how to interact with these tools safely. By following these steps, you are building a foundation. You're ensuring that when the time comes to deploy, you aren't just reacting to the technology, you're leading it. So let's bring it all home. We have covered a lot of ground today, but it really boils down to 4 key pillars. First, remember that CNEC remains your core. Standards like EN 50126, 50128, and 50129 aren't going anywhere. They still provide the RAM's lifecycle, the software processes, and the safety case structure we rely on. AI doesn't change that foundation, it simply extends it. Second, we add the AI-specific governance. This is where ISO 42001 and 23894 come in. Think of 42001 as your organizational rulebook for AI management, while 23894 gives you the specific risk vocabulary you need to talk about things like bias and drift in a professional, structured way. Third, we have the regulatory reality of the EU AI Act. This creates binding legal obligations for high-risk AI, which, as we have seen, covers many of our safety-critical rail applications. But remember, these requirements aren't a separate mountain to climb. They are completely achievable when you align them with the CNEC and ISO standards we have already discussed. And finally, we have the RSSB toolkits. These are your translators. Whether it's T1362 for human factors, T1363 for managing change under the CSM, or T1364 for mapping the standards landscape, these tools take the abstract theory and turn it into practical rail practice. When you bring all of these together, you aren't just checking boxes, you are building a coherent, multi-layered assurance strategy, one that ensures AI in railways is not only innovative, but fundamentally safe and reliable. Thank you for joining me for Lecture 3. In our next session, we'll be putting these frameworks to the test with more real-world scenarios. I'll see you there.
All right, that's it for this session. If you found this helpful, hit the subscribe button and turn on notifications so you don't miss the next one. And quick reminder, make sure you check out the podcast series here on the channel, Rams Ready for Everything Rams, and Safe Tracks for System Safety Assurance. If you're following along with this course, those episodes will really help connect the dots. Thanks for watching and stay tuned for the next one.